So hello everyone. Hey, it's a pleasure to be with you virtually. So I'll be giving some kind of introduction and explain what our goals were, and then Yue-Zhou will take over. I understand that we will be staying around for a period of question after, but feel free to interrupt during the talk as well. So so the main context of our work is trying to understand better what happens at the species scale. So I will start with a brief review of that. So the idea is you consider a theory where you have large number of fields, dynamical fields that are coupled to gravity. It could be ordinary matter, could also be Kaiser-Klein gravitons, various modes. And then the understanding is that in such a situation, we have a cutoff that is lower than the Planck energy to be given by a formula that looks like this. Newton's constant times number of fields times the cutoff, so-called species scale, less than. Okay, so that defines the cutoff of this theory. Okay. And there are various arguments for that. I will just briefly review a few. So it's probably well known to most people in this community, but I would just recall one that I particularly like. So kind of a black hole argument. So if you start with a fireball, a gas that has radius r, and temperature order 1 over r, which is as up as you can make, this gas, it's easy to estimate. It's a relativistic gas. It will have an entropy that's order n, number of fields that are excited, and an energy that's order n over r. And the issue is that if you can make such a fireball that's so small, it's going to collapse into a black hole that could have less entropy than n. So you'll have a violation of the second law of thermodynamics if can collapse into a black hole for which the Bekenstein entropy is in general the area r to the d minus 2 over 4g is less than n. Okay, that's the basic idea. So basically there are too many ways of making such a small black hole. And the conclusion is either that the formula for the entropy of the gas or the formula for the entropy of the black hole must change considerably when the temperature of the black hole rises above this species scale, or its radius gets smaller than 1 over that scale. Okay? That's the usual argument. There's another argument which I like, which would be a bit closer to our logic today, which is to look at the graviton propagator. So suppose you scatter some scalars and you exchange some graviton, and when you have a graviton propagator at one loop level, there's going to be a factor of n that comes from all these fields that can run in the loop. And in principle, you could resum self-energies and so on. And when you resum this, you get an effective propagator that goes like, instead of g over p square, now I get g times n times p to the d. And then say 4, when d equals 4, you get some log. And the basic issue is that when you look at a propagator like this, well, when the self-energy starts to dominate over 3 level, this becomes pathological because it has all the usual pathologies of a higher power kinetic term. It either has negative norm states or it has poles on the Euclidean region. This is pathological. And it's pathological when the self-energy exceeds the 3-level term, and that occurs exactly when this momentum exceeds the species scale. Okay? Those are 2 standard arguments. Maybe let me make a brief editorial comment here, which is that this is really not correct to call this a renormalization of Newton's constant. First of all, it doesn't have the same momentum dependence as the 3-level term. So the word renormalization is simply inappropriate in this context. Just field theory textbook, you only use renormalization when you change things who have the same momentum dependence. But more importantly, that you can actually look at physical observables. And you find, for example, that if you look at a graviton scattering diagram, you will have, in addition, like triangle diagrams. And this triangle turns out to cancel, and say, sorry, I'm doing graviton scalar scattering. You don't have this triangle diagram if you're scattering scalars, but if you're scattering graviton, you do have this graph. And it actually turns out to cancel the observable effect of what we just talked about for graviton scalar scattering. And actually, if it cancels it when you have it on one side, when you have it on both sides, it actually doubles the effect, but it flips the sign. So that's a simple calculation we can do. It's also detailed in our recent paper for graph. So it's not universal at all. So that's one reason for which I find it misleading to call it a normalization of G. And also the other issue is that it's not even gauge invariant for matter particle of spin more than one. For spin greater than one matter. Things that are not ordinary matter, like gravitino loop. You have many KK modes that run in a loop. This loop diagram is not even gauge invariant. So this argument is kind of parametric. It might lead you to suspect that something happens at the scale, but it tells you nothing at all about what actually happens there. And that would be our main question. So what happens at this species scale? And many words have been said about the species scale, apart from the fact that things we know and love break down there. So it's being characterized as an absolute cutoff beyond which any EFT irrevocably breaks down. Okay, I'm gluing together many quotes into one ominous sounding sentence. And our goal will be to try to make that precise and quantitative. More precisely, if what happens at the species scale is really that field theory breaks down, let's just give it a name that describes that. So we're going to call it the QFT breaking scale. Okay, and our goal will be to define this length scale independently of whether n is large or not, whether the coupling is weak or not. We just want to have, in any theory that has gravity, there's some universal cutoff. And above this cutoff, you cannot use any field theory. That's the idea we want to make precise.
So by quantum field theory, you are including gravity as part of it?
Yeah, so it could be a quantum field theory with weak, exactly. So at low energy, you can have quantum field theory coupled to weakly coupled gravity. And that makes sense as quantum fields. And the idea is that this whole framework of a standard quantum field theory coupled to gravity as a field would break down above this QFT breaking scale.
I see, but typically the cutoff of the fields which are not gravitational is different. And it's not necessarily the same as gravitational sector. The species scale is specifically.
So here there's no such thing as a gravitational sector. There's just a cutoff where the QFT framework breaks down.
Right. No, I'm trying to say something a bit more refined. It's true that at some scale something breaks down, but there are some things that don't break down, and nevertheless at that scale. Then the field theory setup might be perfectly fine without gravity included. So typically the species scale are terms which appear in the gravity terms, like the Einstein terms and all that. Einstein squared.
I get your point, but I'm not sure. That's actually I think I view this as a question whether that is actually possible. In what I will propose, I don't have a proof of that, but the sort of line for which we're proving that, it's part of the conjecture about the scale being well defined, is that once you start modifying gravity, then I would expect that everything gets modified, not just gravity. So I'm very.
Well, that's not true. That's not true. We have counterexamples.
We can discuss. That would be a great topic for discussion after. But this idea of gravity sector is something I'm really want to question.
Can I add a comment?
Yeah.
With the weak gravity conjecture or the Tower weak gravity conjecture, then the gauge forces will also become strong at the species scale. So maybe not everything, but there are other things happening there too.
Yeah, they could be. Yeah, exactly. It could be more than one thing, but that still will not affect our definition of that. So gravity breaks down, cut off. That's it. Sorry, field theory breaks down, that's it. And also I want to stress that this is very different from other, I call it a QFT breaking scale, not EFT breaking scale, because normally we're used to the idea that, when an EFT breaks down, it just gets replaced by a better EFT. Like, Fermi's four interaction becomes electroweak theory and so on. But the idea is that above the scale, there's no field theory above that.
Can I ask
this process stops.
Related to that, Simon? So the QFT scale here, you're defining in a fixed number of dimensions, because sometimes what happens, right, with cases like Kaluza-Klein reduction, is that you can have a field theory that breaks down, and there's a field theory UV completion, let's say in one dimension more.
That's a good point. That's my next example. So I want to avoid the word UV completion here, but something that is like so below the higher dimensional Planck scale in the setup you described, you will still have something that I describe as field theory, which is a bunch of weakly coupled Kaluza-Klein modes coupled to ordinary matter. So this below the higher dimensional Planck scale, I would still say you have a QFT, even though it's a higher dimensional one. Okay, so there are two examples. So can this scale be much less than the Planck scale? And from looking at the string theory lamppost, we actually have two well-known scenarios in which that happens. The first scenarios in which that happens is that you can have strings that are weakly coupled and therefore light. So string are weakly coupled, the string scale is much less than the Planck scale. And in this case, we will see later that our definition of a QFT breaking scale will be the string scale. Okay? It differs a bit from the species scale, which has an extra log. So for us, our QFT breaking scale is that. And that really corresponds to the idea that as soon as you start to see the closed string modes of spin 4 and higher, you don't have a local field theory description anymore. Okay? So that's what it would correspond to. And the other scenario to have a low QFT cutoff is to have decompactification. So in this case, as was well known, the QFT breaking scale, so if you decompactify d perp dimension, the QFT breaking scale would be the Planck mass in these higher dimensions, which is also known to be the species scale. For a matter distribution, that scales like the number of KK modes, not just the volume of perp, the volume of the extra dimensions times the cutoff to the d perp. Okay, so if you just plug this formula for n into the traditional formula for the species scale, you end up with a higher dimensional Planck scale. Okay, so that's a famous estimate. And now there are two well-known scenarios. And actually it's been conjectured that called emergent string conjecture. We conjecture that these two scenarios are the only options. So I don't think this is settled at the moment, but I think I personally take this conjecture as a good way to organize my thinking. Okay. And the definition that Yue-Zhou will present it, is actually giving you these answers in these two cases. So I'll say a few words about the way we approach this. So what we study is the S matrix for 2-to-2 scattering of gravitons. So that's a process like that. Two gravitons go in, two gravitons go out. It's very easy to draw. It's very hard to measure. The interactions in gravitons are very small, and maybe with the Jupiter size a crystal that's ultra cold, we can detect gravitons. It's not easy to make a graviton detector, but we can assume it exists, and it's going to be theoretically useful to assume it exists. Conceptually, you could also imagine you're scattering gravity waves, which have a large current state of gravitons, which may be help you thinking in some cases. But mathematically, we study the graviton scattering amplitudes. And at low energies, meaning much less than the Planck scale, and this cutoff, it basically has this form that is a factor of center of mass energy square, S square. And that factor is basically just knows about the fact that the gravity is a force that grows with energy. Other forces will have a different power of S. And this thing comes from like a diagram where you exchange one graviton. So there's a 1 over T from the propagator, whereas T is the momentum transfer. So that's the basic amplitude. We make a few assumptions about this amplitude. Didn't leave myself a lot of space, but I will write it. I'll tell you the assumption and what they lead to. Maybe I can move this a little bit further down below. Okay, so make an assumption, and maybe it's a consequence of relativity. We imagine doing a scattering sign process in a flat region of space. So basically by relativity, this amplitude exists for any S. Including S greater than the cutoff. Okay, so this kind of a, so if you were thinking of space-time as a lattice, sorry, yeah, the question. If you were thinking of space-time as a lattice, it would be weird to look at excitations that have more energy than the lattice, inverse lattice spacing. But the point is that the world is not a lattice, at least that's not what I believe. But if you have relativity, if you have the two gravitons that are well isolated, there's nothing in principle that stops you from having them boosted. Because graviton doesn't have any reference frame. So you can have individual gravitons that have a huge energy, but a small p squared. It's only and so basically the individual gravitons don't know anything about the center of mass energy until they collide. So there's no, if you believe in relativity, there's nothing that stops you from doing scattering processes where the center of mass energy is huge. Cutoff is not relevant. So basically because S does not know, sorry, individual gravitons do not know about S when you prepare them. Okay. And the other assumption is we assume that even when you do scattering at these high energies, probabilities would be between 0 and 1. Okay, that's called unitarity in this context. And so the probability that things scatter would be less than 1. And basically this gives this relation that if you take any 2-to-2 particle state and put the imaginary part of the S matrix as an operator in there, you'll get something that's between 0 and 1, actually 2, with the way it's normally maybe called M scattering operator. With the way it's normally defined with S equal 1 plus IT, the norm is between 0 and 2. Okay? And this psi here is any normalized particle state. Okay, so it's a very simple statement. If S is unitary operator and you write it like 1 plus IM, then the matrix elements of M are bounded between normalizable states. Okay, you have to take some wave packets and so on to make this fully precise, but that statement is a very straightforward, very direct way of saying that the amplitude makes sense at all energies. And finally, the other thing we impose is that there's no time advances. That's causality. And mathematically, the statement that the wave does not advance, a long story, but it basically gives you analyticity. Okay? And again, one might worry about time advances of Planck length and so on, but actually, I don't actually think that there's in terms of retarded time, which is like kind of a null time, I don't think there's actually a limit on the accuracy of time measurements. So So we get this picture, famous picture that's in the standard S matrix axiom, which tells us that in the upper half S plane, we have analyticity. Okay? And using this analyticity and boundedness together, we prove some rules that look like that. And the idea is you do a contour integral that with something that's enough. Yeah.
Quick question. How rigorous, how strong is the link, the implication causality gives you analyticity? How much of it? What kind of amplitudes?
Yeah, so that's a good point. So I think it's a bit of a long story, but I think it's surprisingly hard to prove on shell. Let me say it like this. One thing I can say that I think is the most rigorous thing known so far is that these implications here, the implication of like the sum rules that we talk about, these are rigorous in the DSCFT. And they follow from the causality and the boundary CFT, which is a sharp statement. So the situation where we really know what we're doing is in the SCFT. There's a statement that in the CFT you cannot send signal faster than light. And that's very non-trivial if the signal is going to go through the bulk, that it does not go faster than light on the boundary. And that statement gives you these exact sum rules, but there's some rules that in the flat space limit give you that. So I think that's, if there's one thing we should believe about quantum gravity, it's probably that. At least quantum gravity is that of the sort that appears in string theory and in the SCFT. So it gives this sum rule. And the idea is you start with a contour integral like this and you deform it. And you actually start on both sides. So you deform it to have above minus below the cut. And then you have something below the origin, which gives you poles. So you get a relation between the low energy exchange and high energy, some integral over high energies, which the integral, in principle, the cut can start at 0, but this integral will always be dominated by high energies. So it really gives you a relation between gravity that you measure in the IR from G Newton and some UV averages, okay, which is standard thing that people talk about now. But specifically in the form of these sum rules, Kramer's Kerny type sum rules. Okay? And maybe I will say a few things before passing to Yue-Zhou. Maybe I will say a few things about the nature of this amplitude. So one thing which is often common to do is to look at the amplitude as a function of energy and impact parameter. That would be something like 1 over 2s times integral of over momentum transfer of the scattering amplitude at that energy and momentum transfer is just a Fourier transform. And I'm missing some factor of 2 pi, and you have some Fourier transform like this. And the probability that you don't scatter is this. Maybe let me like that. 1 plus IM of SB is approximately the same, but it's actually exactly the same as the partial wave as a scattering amplitude for a given angular momentum and energy, where the angular momentum is the impact parameter B times center of mass energy divided by 2. Okay, that's just the angular momentum of the scattering process. That's the elementary calculation. Okay, and so there's relation between the partial waves and the amplitude. And I just want to say, if you think about this, because so in the deep UV, so clearly this is bounded. And just because it's bounded, then integral of ds over s cubed of stuff will be dominated always by the lowest energies at which you get something non-zero, okay? And the idea is that this energy will be basically this QFT breaking scale. Okay, that's the idea that the proposal that Yue-Zhou will elaborate on is that we can define the QFT breaking scale from the energy scale at which these integrals get dominated. Okay? And I want also to note something else, that at very high energy, it's often said that this will become exponentially small. So actually what gets exponentially small is S goes to 0, and it's expected to be proportional decay exponentially with the Becken-Shanghai entropy, which means that the probability of survival, if you take the two particle states, the probability it does not create a black hole is expected to be exponentially small. But for us, that just means that the amplitude goes to I, MSB. And this region will not actually matter for us today. Because this behavior happens at energies that are much above the place where the sum rules will be dominated. Okay. Okay, so I just want to say that.
So can I ask a quick question?
Yeah.
So we have examples of quantum gravities where we believe there's just like some massless fields, and then there's nothing on the spectrum until the Planck scale, until that contribution starts being a 4-to-1. Like you have black holes.
Yeah, exactly. So in this situation, this integral will be dominated by Planck scale black holes, whatever you call them.
Okay. So that's what you mean. Okay, thanks.
So we're not going to assume that this integral is dominated by something close to cutoff. That would be a decompactification limit or something like that. But generally, there's always going to be some scale where this integral is dominated. Okay.
I have another very general question, which is just this amplitude that your scattering amplitude has infrared divergences because of the massless graviton. So
Yes.
How do you deal with that?
Yeah, so I have a few answers to that. So one of them is that well, there's one case, for example, if the QFT breaking scale is much less than the Planck scale, and below the Planck scale, this coefficient of the infrared divergence is completely negligible because it's a Planck suppressed effect from graviton scattering. So we can neglect this. Something else I can say is that when you uplift the situation to ADS4 CFT3, the IR divergence just become control logs of RADS over the energy scale you're looking at. So there are statistical situations where you understand perfectly what this infrared divergence do. And it's basically just because when you scatter, they're very simple. Just because when you scatter things in and there's gravity acting between them, you get a Shapiro time delay from that. And the further out you take your initial object, the more Shapiro time delay you get. So if you try to make a constraint that tells you that there's no time advance, then like this larger and larger, then this divergent time delay makes your constraint slightly weaker. But if you're in ADS, you can control exactly how big the Shapiro time delay, and there are situations where it's negligible.
I see. So it doesn't end up mattering.
I don't think so, no. But thanks for this question. So I will pass on the microphone to Yue-Zhou.
Before you do that, let me just to make sure I understand the logic. So if you define the species scale as the scale in which this amplitude is dominated, no? I mean, why is this equivalent to the scale at which the QFT will break down for sure? Like,
that is not yet obvious, and in fact, the definition will not be exactly that. The definition will have to do with having high spin contribution to the sum that overwhelm the low spin that are large in some sense compared to low spin. So usually we'll describe the precise definition shortly. So somehow it will have to do with this sum being high spin sensitive. We call this high spin onset. Okay. So let me pass it on to Yue-Zhou.
Thanks. So I'll share the screen. Okay, thank you. Thank you for having me. So I continue Simon's talk, and probably first, again, just to review a little bit gravitational sum rule, because this is very important in the following discussions. So the idea of the sum rule, as Simon explained, is to relate the no-energy field theory to some unknown possible UV completions. And people recent years use this fact to constrain the allowed space of no energy effective field theory and so on. And the idea is that we have this amplitude and we assume some high energy behavior so that we can just make a large arc in the complex energy plane. And this arc integral is vanishing. And so, because as Simone expand, we assume that the causality, and causality is equivalent to the statement of the elasticity. So we can just deform the contour to make it into two pieces. First is to have a small arc along the no-energy region that we can apply some local field theory description and so on. And the second part is some integral along the high energy part, which is we probably string theory or some other UV scenarios that we don't know, we don't assume. So now, if we just apply this gain to the Einstein gravity, then the energy parts we can just we can measure the Einstein gravity using the sum rule and energy that measures the G Newton, and all other contributions like unlearned UV physics or loops, something can be organized into the high energy part by using the partial wave decompositions. That's saying that we don't know much more details about that, but one thing we know is that by Lorentz invariance, we can decompose the amplitudes into the partial wave. And by unitarity, we know there's the imaginary part of the partial wave coefficient, what we call the spectral density, has to be positive definite. So once we do this, we then have an equation to relate the G Newton to some UV physics. And this UV physics can be schematically organized in terms of the positive coefficients multiplied with some other functions in some over some states. Yeah. So then we're ready to show what Simon just said about this phenomenon of the high-speed onset. The idea first we want to show is that we just start with this sum rule. And one way to do is we can smear this sum rule with some toy with functions that defined in the impact parameter space. So this is basically the function that we study. And now we can just evaluate the sum rules for no energy gravity and for some other loop effects from no energy weakly coupled matters. So for no energy gravity, we see that this picture is in 4 dimensions. So for no energy gravity, we see that it behaves like logarithmic in the impact parameter. So it's quite flat in this plot. However, whenever we look at the one loop contribution from matter fields, their contribution actually decay very fast. So some comments is that first, from the dispersive sum rule, we know that the one loop contributions with some unlearned positive contributions from the UV physics must add up to reproduce an energy Einstein gravity. And that's basically what this equation tells us. So if we know this, then the idea is that the maximal budget allowed by Einstein gravity and very no energy that gives us something like the species bound. The rough idea is that we can choose the number of particles, the number of light matters, so that at no energy they add up to saturate the budget set by the no energy gravity. So this is those numbers give us so that this curves at very no energy and no impact parameter, it saturates the Einstein gravity, and this is something that that gives us the species bound. But the idea that the dispersive sum rule says that the energy gravity has to be reproduced at all impact parameter and all energy if we sum up those sum rules at high energy. But as we see here, that all the computable loops have the wrong shape at higher impact parameter. So the idea is that all those curves decay very fast at higher and higher impact parameter, that is higher and higher spin. So this means that to get the knowledge gravity, one must require significant large contributions from higher spin. So this is what we call the high spin onset. And we think this provides us the intuitive way to understand this species bound. So are there any questions so far?
So can you quantify this? Namely that there are constraints and there are many possibilities. So you have to exhaust all the possibility to have constraint, right?
Sorry, I'm not sure I understand what you mean.
Well, so there are many choices you can make. So you can have, for each spins, you can have so tower of massive particles, for example. So
Yes,
it
yes.
looks like you have infinitely many parameters to work with. And how do you give some kind of precise bound implied by this sum rule?
Oh, yeah. So, yeah, I actually skipped the details, but in these slides, I show an example of the precise bound. So this is the, we have the sum rule. So maybe I try to explain using the slides. So we have the sum rule, and actually there's some energy contributions that we can measure the number of light particles from the sum rule, and then we try to cook up some functional that make, I mean, you use the positivity to bound this number of particles and try to optimize those functionals. That's basically similar to the bootstrap idea. And this is what we get for the light particles, like if we assume some cutoff that QFT breaking scale is capital M, and then this is the bound that we get, a sharp bound that we get numerically using the bootstrap techniques for the mass around the 0.1.
Would you explain the notation, what N0, N half, N1, etc.?
Oh, yeah, sorry. So those are number of light particles with spin. Like this spin 0, spin 1/2, and spin 1, spin 3/2. And
do you assume they all have the same mass? Or?
Yeah, in this case, we take to be the same mass. Yeah.
And you only consider this finite number of spins. You don't consider massive higher spin particles in the.
It's because this is an energy. So we define this number in the energy regime that we only count the.
Yeah. So I understand that if you limit the possibility, then you can write this kind of nice finite inequality. But there are infinite possibilities. So how do you control?
No, this is all the possibility. If the assumption is that we're talking about field theory. So as soon as you have a higher spin particle, more than 2, you need to have an infinite tower of them, and you're no longer doing field theory.
Yeah.
What you're doing is something else. Maybe you're doing string field theory or something else, but it has a different.
Oh, so you are not considering such a possibility in this context.
Well, higher spin particles will appear, but we'll just call them other. But the things field theory, by definition, this is the most general thing you can have. That's a definition of field theory. That's our definition.
I see. So you're considering something strictly describable in terms of field theory plus graviton.
Yeah, this is an energy regime, the energy description that we want to construct.
So are you saying elementary higher spin particles? Because surely you can have composite higher spin particles in field theory.
Yeah, that's a good point. But this is not. If you have, for example, something that's a bound state of quarks, you should just put the quarks in the loop. The bound states don't really. That's not the proper way to deal with them. So you never. It's never correct to treat these bound states as fields.
So I'm a bit confused. What do you mean by N2 of a massive spin 2? What do you have in mind then? It's graviton. It's not graviton for you, obviously.
It's not graviton. Yeah. It's
KK mode of graviton.
It's KK mode, like massive spin 2 field.
Well, if it's KK, then you have an infinite tower of them. It's not that either, right? So what is it for you? I don't have any working model for this kind of example. That's what's confusing.
So N2 will be the number of KK modes below your cutoff, and you can replace this model of same mass by a power law distribution if that makes me happier. You'll get a similar number.
So this is you talked about the emergent string conjecture. There are 2 possible limits. This could only apply to the KK context, correct?
Yeah, exactly. You could only have a large N2 if you're on the compactification scenario.
Okay, thanks. So you're specifically talking about that particular scenario.
Yeah. Mm-hmm.
But if you had some confinement scale right below your species scale, then shouldn't that be accounted for? It doesn't seem like it's one of these numbers.
No, it's still, even if you have confinement scale, summing over all the meson that can run in loops is never a correct way to calculate you should
What
use
is the correct way to
at high
calculate?
energy, you should use the quarks and gluons or whatever are confined. You should
You're
not
saying
do-
you only care about the high energy part. You don't care about
Exactly. This is high energy scattering.
Okay.
Thanks. So this is an example of the numerical bound that we can get for the no energy light particles. And let's just go back to the high spin onset, because this is the concept that we want to emphasize. So we want to make this deflation sharper. And one way to do that is we want to look at it spin by spin. So based on the impact parameter, some rules that I told you before, we define electron objects is that we take the partial wave coefficient and do some moment integral along the energy to some scale. And then we suggest to look at the ratio that basically just compare this moment with its higher spin counterpart, like for example, J plus 2 over J. So this is the thing that we will study. And although this analysis is mostly performed based on perturbative calculation and no energy loops, this moment ratio is in principle, the comment is that it is in principle valid non-perturbatively, because it is about the data extracted from S matrix. And as Simon said, it's when we just define the S matrix, we actually don't need any field description or weakly couple assumption and so on. So it can be defined non-perturbatively, and it can be used to define universal quantum gravity cutoff that we will just mention a bit later. And in this way, we can have a non-perturbative deflation of that scale and concepts of the number of species. So here is our deflation. We define the high spin onset scale that we call lambda O, lambda onset, as the lowest scale.
Is it just me who lost the screen?
Sorry?
I can still see the screen.
Too small or?
You can see the screen? Oh, I'm sorry. So maybe I should.
Sorry, what's the? I'm confused.
I think you can continue.
Oh, yeah. Sorry. So we define this high spin onset scale as a lowest scale at which we have this ratio to be larger than some order 1 number. We don't know what's precisely the order 1 number. That may depend on the different UV scenario, but this is a rough idea that we define the scale. And the statement is that this onset scale is the universal scale in which local field theory break down. So let's just justify those points in focusing on 10 dimensions with supersymmetry. So we can analyze this 10-dimensional supersymmetric partial waves from different models. So we can see when we take those models with nice UV property, like some bootstrap strongly coupled amplitudes or the tree-level string amplitudes or some Icolo model, they all, when we compute those moments, they all like pretty flat when we go to higher and higher spin. But if we just look at the one loop contribution from supergravity, then it decays very fast. So this means that this means that all the UV models, such as string theory or non-perturbative bootstrap amplitude, all satisfy the criteria since they have very rich high spin contents. So that's what we mean the high spin onset for the UV theory. And the onset scale, and so we will also show that the onset scale is indeed qualitatively either string scale or the higher dimensional Planck scale, which is the statement that is consistent with the emergent string conjecture. So this is that we can just roughly take the ratio, this number to be 0.5, and we can estimate a different scenario that can give us either the the onset scale is like square root of 2 of the string scale, or the 4 pi multiplied with the 11-dimensional Planck scale. And here's what we can see. So again, we just, for example, take the superstring amplitudes and compute the ratio of the moments that we define, and look at the ratio, for example, G4 over G2 and G2 over G0. And we can look at this curve and find that the ratio becomes order 1 and saturate to be like order 1 at some point, basically around the string scale. And the second thing that we can do is we take the work by Patrick Virel, Jerome Pendleton, and others, where they bootstrap the 11-dimensional M theory amplitudes for graviton scattering. And we can take that and do the compactification into the 10 dimension, and then again compute these ratios of moments. And then again, for this plot, we find that the ratio becomes order 1 when we go to the energy roughly the 11-dimensional Planck scale. So this is 2 scenarios that we show. This is with supersymmetry, but the supersymmetry is actually not crucial here, because without supersymmetry, we still observe the same phenomena. Like this plot, we show the general 10-dimensional moment. And for string theory, this moment is all like pretty flat when we go to higher spin. But for all the computable one-loop contribution from like matters, they all like decay very fast. So there's a huge gap we have to fill in with a bunch of tower of higher spin. And in higher dimensions, we also have other representations, and they basically say show similar pattern, but this is not very important. So so far, I just basically show the main idea. So yeah.
Yes, a quick question. When you
yes.
have the plots, choose lights before?
You mean this?
Yeah. What are the meaning of the numbers that you have like in the lower?
Oh, yeah. So this numbers is that, so again, when we try to compute the energy loops, we have one parameter to change, that is the number of particles. So if we change the number of particles, this curve can just move up and down and so on. So this number is chosen so that they all like basically at one point to be the same.
Can I ask a related question? So this is follow up on the question I asked earlier. So the constraint you are getting is rather similar mathematically to modular bootstrap constraint, where you have also infinite number of representation of Virasoro algebra, and then you put some kind of constraint. These are linear equations, and so this is also linear equation. So in that case, it is possible to derive a variety of like universal inequalities without assumptions. Here, so far I have only saw examples. Can you actually write down some kind of universal inequality that constrain the spectrum of these particles? So far you presented, you try to convince us based on examples.
Yeah,
and I'm asking whether you can actually write some kind of universal inequality applicable to all possible arrangement of higher spin particles.
I think there are 2 things that can be made there. So one thing is that to define the onset scale, these numbers that you see on the slide are completely irrelevant. The only thing we need to define the onset scale is to look on this plot at the ratio of the spin 6, the spin 4 contribution, and put any number which separates, put any threshold choose any threshold that separates the matter from the other things. So the conjecture is that even if you have an interacting QFT or anything, the conjecture is that you can make a bound that will be somewhere between these in this gap. There should exist a number that continues to separate.
Yeah, but this is a mathematical question, right? So this is a linear problem. So
no. For the linear problem, the linear problem is not well defined, because I'm also not sure exactly what you mean in the 2D CFT case, but here it's definitely not defined, because N is like here the idea is that, okay, let me explain how this relates to species bound, right? This is basically telling you that as far as the species bound goes, roughly speaking, 64 spin 2 particles is like a million scalars. Okay, then not species are counted equal. Okay, that's what this number means. But the thing is that we basically at the moment we don't see how to give a precise species bound, because the number of species is not something that's sharply defined. The thing that is sharply defined is the onset scale, but how many species there are below the onset scale is fundamentally murky, because the species that are very close to the cutoff, we cannot trust the one loop approximation. We don't know how to calculate anything about them. So the concept of counting species is fundamentally ill-defined. So we cannot give a sharp bound on the number of species. The only thing we can give a sharp number on is the onset scale.
Okay, yeah, I think I should need to understand the detail of the calculation. Thank you.
Maybe a related question is, it may not be particles. Like you could have a CFT coupled to gravity, for example, right? So it would be interesting if you could rephrase this in terms of, some, I don't know, like not maybe a central charge, but some generalization to QFT of something about like how much stuff is there in the matter sector, right? Like it seems like there should be something that tells you how is this affecting the gravity calculation.
Yeah.
Something more general than just, how many particles of each spin do we have?
Yeah, that's a very good question. That's one of the open questions we leave. So basically for low spin matter 0 up to spin 1, for the 3-point function, is known that the 3-point function of stress tensor, which is the thing that is being probed there, 2-point and 3-point functions are a linear combination of those for free fields. So, and then you just replace the count by some central charges. But what we're really probing here is also the 4-point function. So it's not known to what extent is the 4-point function of a generic CFT, a linear combination of those of free fields. This is a well-defined question.
Thank you.
Thanks.
So I think I just summarize soon. I hope we convince you that the high-spin onset scale is the right way to define the scale where local field theory descriptions become invalid. And it is in principle a non-perturbative definition. So we expect to work for finite G Newton. So the summary is that you summarized what Simon said and what I was just describing. We analyzed the one loop contributions from massive fields to graviton. Sorry, the contribution from massive fields to graviton scattering amplitudes. And using that elasticity and unitarity, we find some numerical version of species amount unlike particles that is defined very at no energy much lower than the QFT the onset scale, so that we can have a well-defined number. Then we perform the partial wave analysis in high dimensions and observe that the UV scenarios all exhibit significant high spin content compared to the matter loops. So in this way, we define non-perturbatively the high spin onset scale, beyond which local field theories irrevocably break down. And it coincides with the string scale and higher dimensional plane scale, providing further evidence of the emergent string conjecture. So I'll just leave some questions for the discussion session. First, that I think probably very important to understand better is that once we have this definition of the high spin onset scale, what can we do with it in the future and use that to understand the rate of change of the cutoff along the moduli space and something related to the recent observed pattern. To ask this change can be defined by the tree-level 3-point coupling between a light scalar field and 2 higher spin states at the onset scale, at the high energy onset scale. in a similar way like the Yukawa coupling sets the fermion mass. And the second question is that like just the question that just asked is very important thing is the how matter-matter interactions modify the shape. And in this way, we might want to compute the stress tensor for point coordinators in QFTs or CFTs or conformal field theories without adding gravity and compare to what we have now, and it's probably related to the conformal fixed point versus the gravity UV completion something. And perhaps if there is a similar mechanism for the magnetic wave gravity conjecture, because it also defies the scale that is less than order one number multiplied with the Planck scale and Yamia's coupling. And another question that I find very curious is that if it's possible that we can see the high spin onset phenomena or define the high spin onset scale by just looking at small black holes and with some entropy arguments and so on. Yeah. Thanks.